So now we have a call to the next generation of magnetic engineers, magnets without sparks, Dr. Marc Thompson and Sophie Thompson.
I don't want to get Microsofted. My name is Marc Thompson. It's been my honor to teach here on and off for the past 15 years. I'm going to talk about magnetic stuff, hopefully without sparks. Because when you have electromagnets, anytime you have a spark, that's a bad thing. So the topic of my talk is basically why magnets are cool. Magnetics versus electrostatics. Here's electrostatics: high voltage, relatively low current, and sparks. High voltage, low current, and sparks. Now in the magnet world where I live, we want high current, low voltage, and no sparks. Sparks are bad. It means your transformer insulation is breaking down. Usually something bad happens, like a fire, when that happens. We don't like that. So no sparks. Maxwell's equations, don't get scared. They explain electricity and magnetism. Maxwell was this crazy Scottish genius that figured this stuff out more than 100 years ago. He actually didn't figure out all of the Maxwell's equations himself. He put them all together. He fixed a mistake that somebody else made, and there was light. Electromagnetic waves were born. And here is Maxwell's equations. It's an old joke, but the joke I told last year is this girl must have gone to MIT to have Maxwell's equations tattooed to her back. Well, there's 4 laws. Gauss's electric law, which explains how Professor Emanuel's sparking works. Faraday's law of induction, which we'll get to in a little bit. Ampere's law, and Gauss's magnetic law. So we magnet guys work with 3 out of 4. However, this tattooed young lady has a problem. There's a mistake. She left off the J. Her tattoo was for Maxwell's equations in free space. When you have J, which is current, then you can have electromagnets, so I need the J. And I'm going to show you electromagnets here in a little bit. Now, here's a question. Why do magnets attract or repel each other? Nobody really knows. We know what it does, but we don't know why it does it. This question was put to Professor Richard Feynman in an interview, and I have a little clip, and it seems like he got a little bit annoyed with the interviewer.
In the world, the existence of magnetic repulsion, or electrical attraction, magnetic attraction. I can't explain that attraction in terms of anything else that's familiar to you.
He's basically saying, look, we can think about
Take as an element in the world, the existence.
Let's try this. He's basically saying, unless you really delve into quantum physics, we don't really know why it does what it does. We know how it does what it does. And he got a little annoyed with that question. And when you have a Nobel Prize, you're allowed. So why become a magnetic engineer? That's what I do for a living. I teach part-time here at WPI. You do magnet stuff, you can do all kinds of cool stuff. Some of it's kind of messy, which I was playing with here before. I'll show you some ferrofluid, but you can do magnets and motors, magnetic levitation. We're going to levitate something later on. I'm going to show you some magnetic fluids. And next I'll show you a few examples of some fun things that I've been interested in. I've done a bunch of work in maglev, and I was sent to Florida a year ago to test a magnetic levitated train. As part of this test, I was able to have them levitate the train, and then I told them when to stop levitating it. While it was levitated, basically a controlled crash. And I'm going to show you a controlled crash next. It's me standing out in front of the train. It's levitated now, it's coming this way. And then they shut it off and crash it and let it skid. That's pretty cool when you get paid to get somebody to do that. And you even get to ride inside. I'm the videographer, so I take responsibility for the poor video.
6, 7, 8, 9, 10.
Boom.
All that stuff.
Again, I got paid to do that. What else can you do? Now, the next thing I'm going to show you, I didn't do, but I wish I did. That's to levitate a grasshopper at the 16 Tesla magnet in the Netherlands. Now, how does that work? You folks are probably familiar with how a permanent magnet sticks to a piece of metal by magnetic attraction. Here's a permanent magnet, here's a piece of steel. Well, there's another phenomenon called diamagnetism. It's where things are repelled by very strong magnetic fields. And water is very slightly diamagnetic. So inside the grasshopper there's water, and the grasshopper is pushed from all directions, exactly offsetting his own weight, and he sits there and floats. There he is again. All right, if you think I'm mean to insects, we can be mean to frogs as well. Now, all you need to make this work is a 16 Tesla magnet. You have any idea how strong a 16 Tesla magnet is? The Earth's magnetic field is about half a Gauss, and there are 10,000 Gauss in a Tesla. So you do the math, and forces go as magnetic field squared, so you do the math. There are more mundane things you can do. Professor Eric Laithwaite was a famous professor in England that did much of the pioneering work on induction motors. And I have a video here of him levitating an enormous piece of aluminum.
And this time we're going to do it at 400 volts with a higher lift, and I'd like you to notice the increase in lateral stability. Okay, switch on. Now I can practically take hands off. It's just on the point of becoming laterally stable.
Maybe we ought to ask the dean if there are funds available to build one next year here at WPI. How does this work? Well, you apply a 50 hertz field, in the case of England, to the aluminum, and it creates eddy currents and lifts up. That's pushing off magnetic levitation. The next thing I'm going to show you is kind of messy, because I'm going to try to do an experiment in real time, and I'm also going to show you a video of ferrofluid that I did in my lab. Ferrofluid is this gunky stuff in this jar. This is about 20 bucks for a bottle. It's tiny little nano-sized particles of iron that are coated with something called a surfactant, so they don't all clump together, and it is attracted by a magnet. So what I have here is a very high-strength neodymium iron boron magnet. Do not get this near your wallet or your hard drive, because it will erase it. or your credit cards. I've done that. And here, I have this gunk that gets all over everything, right here. Now, just to show you I'm not all mean, you can levitate a strawberry as well. No strawberries were injured in this experiment. Another fun part about knowing a little something about magnets is that everybody likes them. So I get invited to go to the school in my town every year and do a presentation that I call Stupid Magnet Tricks. Basically going in, showing the kids electromagnets, and I levitate things for them. And after the last show, the third graders made some nice pictures. See if you can identify the magnets in the pictures. That's a battery on the right, a nail, and it's an electromagnet. And we lifted up paper clips with it. I don't know what this one is. This one is a magnet stick picking up pieces of iron, metal things. These are, I think, refrigerator magnets. This is this coil levitated, which I'll show you in a little bit. And what magnet is that? It's the biggest magnet in the world, which is the Earth. And the kids really, really like that. We say, what's the biggest magnet in the world? Well, it's the world. The North Pole and the South Pole are actually magnetic poles, or something close to it. And one of the students drew the biggest magnet in the world. And of course, I think that sort of sums it up. Next, we're going to do something completely different, continuing our education, our engineering education. I'm going to show you an instructional video on how to change a light bulb, followed by a short quiz. Okay.
Hi, replacing a light bulb is one of the simple things to do. The first thing you need to do is to remove the broken bulb. First, we have to make sure that the bulb is not too hot. Now that it's not hot, we can unscrew it. Oh. Sometimes when you use a lamp for a long period of time and it goes through a lot of temperature cycles and the screw part is rusted, when you try to unscrew it from the fixture, the screw part can break off the glass part and get stuck in the fixture. Just make sure you don't cut your fingers and take the screw part out. My finger.
It's harder than you think to change a light bulb. Okay, now I need a volunteer to answer my quiz about engineering. Let's have the smallest engineer in the room come on up. I see a small engineer right here. Turn around. Can you tell everybody your name?
Sophie Thompson,
And how old are you?
9,
And what do you do for a living?
nothing.
Well, every time I've had an assistant, I've called them Igor. So I'm going to call you Igor. Is that all right?
Yeah.
Okay, now I'm going to give you a quiz. Here we go. Pay attention. How many software engineers does it take to change a light bulb?
I don't know, Dr. Daddy.
That's a hardware problem. Are you ready for your next question? Face the audience. How many hardware engineers does it take to change a light bulb?
I don't know, Dr. Daddy.
None. We define darkness as an industry standard. You got this? Okay. How many magnetic engineers does it take to levitate a Barbie doll using the Floater Rider trademark magnetic levitation system?
One, and that's me.
Excellent. Come on up and let's do some levitating. Now, Igor, do you know about Faraday's law of induction?
No.
Faraday's law of induction says that if I have a changing magnetic field, as might be created by a coil, such as this, and if that changing magnetic field hits a piece of aluminum, it generates a voltage and a current and a lift force. So, why don't we levitate the small coil first? So we're going to plug in So here we have a variac, a variable auto transformer, and 60 hertz current is going into my coil, and I'm going to use the pen just to keep things from hopping off, because this thing is like a puck on an ice hockey table. It wants to fly off. So can you turn on the variac and give me some juice? A little more. That's good. You see this? Oh, turn it off. Try it again. Good. Now turn it back down. Now, how high does it go? If you put more current into it, give it a little more current, it goes up. And why is that? Because you're generating more magnetic force. Turn it back off, please. When you turn up the current, you generate more magnetic force. The coil lifts up, and then as it lifts, there's less magnetic force because it's further away from the aluminum plate. It takes about 300 or 400 watts to lift this coil, so it gets kind of warm. Now, next thing we're going to do is we're going to levitate the Barbie doll with two coils. There's Barbie. Whose Barbie doll is this anyway?
Mine?
So you don't want it hurt. Okay. Usually when I do this experiment, some little boy in the class will say, "We want to see Barbie blow up." So now there's two coils. One is going to push this away, and the other is going to push this away. And that's why there's a V-shaped channel. So this V-shaped channel produces both lift force and a stability sideways force. Okay, are we ready, Igor? Go ahead. Huh. Oh, what's the problem, Igor? Oh, turn off the power first. And all right. Are you ready? And there she is, levitating Barbie. Can you turn it off, please? So I just have one last question for you, Igor. Are you afraid of magnetic fields?
No.
Good. You are my daughter. Thank you for your help. So if you could take a snapshot of the magnetic field lines underneath the coil, you would see the magnetic field lines get squished up underneath the coil. And that's a result of the induced eddy currents in the plate on the right-hand side. So this experiment works at 60 hertz, but it does not work at DC, because at DC, the field goes right through the aluminum plate and doesn't do anything. So that's not very interesting. So that's why we use 60 hertz. 50 hertz would work okay as well. And that concludes my talk. If there are any questions, I'd be happy to take them. If not, we can go to the next speaker. Thank you very much.